All right, so colligative properties. Let's talk about what a colligative property is then, okay? Colligative properties are those properties that are resulting from the number of particles of solute in a solvent and not on the nature of the particles. Okay? Colligative properties are those properties resulting the number of particles of solute in the solvent and not on the nature of those particles. So let's talk about what that means then. Okay, I've got a solution of some kind. Let's just draw an illustration of a cup here. Okay, and so I've dissolved something in this solvent. And most of the time we use water as our solvent, but it's not the only possible solvent. Okay, in fact, if you're looking at the hardware store for a solvent, you're probably not going to find water. You're going to find some kind of organic solvent. All right, that's a different thing altogether. But you're dissolving solute particles in solute particles in solvent particles, okay? And those particles have attractions. Now, they might be the kind of attractions you have between nonpolar substances, and those are called London forces. You might have the kind of attractions you have between polar substances. Those are called dipole-dipole forces. You might have the kind of attraction you have between an ionic solute and water, which is a polar solvent, okay, which would be something kind of even beyond dipole-dipole, where you have actually charged particles attracted to dipoles. All right, so all kinds of attraction between particles, but it's much like what we talked about with gas laws in the previous unit. We said all of our gas laws follow what's called the kinetic molecular theory of gases. And in the kinetic molecular theory of gases, we assumed that those particles in gases don't have attractions. That was part of one of the assumptions or postulates of the kinetic molecular theory of gases. Okay? There is also a kinetic molecular theory for solutions. All right? It is the same kinetic molecular theory, but we usually differentiate them. I'm not going to make you memorize postulates or assumptions for the kinetic molecular theory as it applies to solutions. Okay? But I do want you to remember that one postulate about particles attracting, because that is what really affects what we're talking about here. Colligative properties ignore interparticle attractions. Colligative properties ignore interparticle attractions. So we're assuming when we're talking about colligative properties that there are no attraction between particles. We're only looking at those behaviors of solutions that result from the number of particles, not on the nature of the particles, because it's the nature of the particles that results in that interparticle attraction. You get where we're coming from here? All right. So there are a number of colligative properties. All right. We've already looked at a couple of those. We looked at boiling point increase and freezing point depression. Both of those, boiling point increase and freezing point depression, use the same equation. Delta T equals I, and there's the number of particles right there. That's why we used I in our equations. I times the constant times the molar concentration. Remember that? Okay? So this I, the Van Hoff factor, can mean more than the number of particles. That's what I told you in the beginning, that we assume it to be something simpler. And so for high school chemistry, we only look at the number of particles here. That's what I stands for. And that's how we did math for colligative properties. So when we calculated boiling point increase and freezing point depression, we were assuming the kinetic molecular theory as it applies to solutions, and we're assuming there were no interparticle attractions, when in fact there are. And so if we used I the way it probably ought to be used, we would have to also have a factor in there or a change in there that would take into account interparticle attractions. Okay? And I is often used with interparticle attractions. We don't use it in high school chemistry. All right, so boiling point increase and freezing point depression are among the colligative properties. Okay? Let's see, colligative properties. So I want to go back one here. Colligative properties. So among them are boiling point increase, and freezing point depression. And of course it left off a D. It should be depression. Come on, D, tight. There we go. All right, freezing point depression. Now then, let's go to something called osmotic pressure now. Oh. Let's try to take our minds back to the very beginning of the previous unit, okay, when we're talking about gas laws. And I took you out in the hallway to illustrate the concept of pressure. And we used little plastic balls, and we had a target up there, and I showed you how banging of molecules, those balls representing molecules of a gas, banging of those molecules against a surface area is what pressure is. Because pressure, by definition, is some force applied to an area. The definition of pressure, as far as the math is concerned, is force applied to an area. Okay? Well, there are a couple of colligative properties we're going to talk about now, starting with osmotic pressure, which have to do with pressure on a surface area or an area of some kind, where the particles don't bounce off. They go through. Okay? So osmotic pressure is about particles going through. Osmosis, you've heard that term before, right? That's what we're talking about here. You've heard in your biology classes about selective membranes, right? Your cell walls are selective membranes. Some things can go through and some things can't, right? Well, when you have an imbalance in the number of solute particles, say the outside of your cells have more salt particles, more sodium and chloride ions than the number of sodium chloride ions than are inside the cell, that's an imbalance, okay? And that exerts a pressure on the cell wall. So those selective membranes, called an osmotic barrier, those selective membranes can have a pressure, excuse me, due to the concentration of solute particles. You following me here? Okay? So, if you go to the hospital, and by chance, we just happen to have a colleague here who's in the hospital right now, and so she's got IVs in her arm. And those IVs have to have the right concentration of salt, or it would kill her. It would kill you if you're in the hospital without the right concentration of salt. So they'll be using an IV to give you intravenous fluids just to keep the fluid level up, in your body, or they're going to be administering drugs through an IV. But the salt in the IV has to be the right consistency, the right concentration, or it will kill you. Okay? If you put pure water in somebody's veins, it kills you. All right? The reason is, if you don't have enough salt that you're putting into the bloodstream to balance the salt inside the blood cells will rupture because it's trying to equalize the concentration of salt. If you put too much salt in the IV, the blood cells dry up, and that kills you too. Okay? Not a good thing. You have to have the right concentration of salt in that water to keep everything healthy. Okay? So then, osmotic pressure then is the minimum pressure which needs to be applied to a solution to prevent the inward flow of water across a semi-permeable membrane. The minimum pressure which needs to be applied to a solution to prevent the inward flow of water across a semi-permeable membrane. Now, all of these colligative properties we're going to talk about today, all these colligative properties behave the way they behave in an equilibrium system. So we talked about equilibriums before. Okay? These are all equilibrium systems we're setting up. So in osmotic pressure, let's just say that this is our osmotic barrier. Okay? This is our osmotic barrier. All right? So an osmotic barrier, and while that word-for-word definition I gave you a minute ago is great to have on paper, it doesn't really tell you the underlying concept here. I want you to understand the underlying concept here, okay? If I have an osmotic barrier here, and let's say I've got water on both sides of the barrier, okay? Because you'll have that a lot. Your blood vessels, your blood cells all have water inside and outside. So here's our water molecules inside and outside. So I've got the same amount of water on both sides, or the same number of particles on both sides overall, because that's a pressure as well. If I had more water on one side than the other, it would exert a pressure. But let's say we have the same amount of water, the same pressure of water on both sides. But on one side, in addition to that water, we've also got something else. It could be sugar, it could be salt. We've got some other kind of particles stuck in here as well. Okay? This creates a kind of pressure as well. All right? The system, the equilibrium system, wants to have the same, not only the same number of water molecules, but the same concentration of these dissolved particles on both sides. Okay? If you don't have the same number, then that increases the pressure, the osmotic pressure. That makes sense? So what happens is that this water on this side, let's just say that this barrier is selected for water. That's to say, the water can travel through, but these dissolved particles can't. They stop. That makes sense? The water can travel through, but the salt particles or the sugar particles, whatever they are, cannot travel through. You with me? All right. So what's going to happen is this equilibrium system is going to try to move water molecules through until you have the same concentration of these dissolved particles on both sides. Now, if you can't move any dissolved particles on both sides, it'll keep moving water through until there's no water anymore and it dries up. Make sense? Got that? Now, if this side over here is inside your cells, your blood cells, your blood corpuscles, they're called sometimes, then you're going to build up so much water over here, they're going to explode. That's why putting pure water in your blood through that IV is not a good thing. On the other hand, if you have too much salt on one side or the other, it's going to dry up. Or if you put too much salt in the IV, by the same token, the water's going to try to equalize out. You're going to move water out of the blood to try and equalize the amount of concentration on both sides, and the blood cells dry up. You get it? That's what the pressure is all about. Okay? So when we say that osmotic pressure is the minimum pressure needing to be applied to a solution to prevent the inward flow of water across the semi-permeable membrane, Water is mostly what we're talking about here. You do have other kind of semi-permeable membranes, okay? Most of the time it is water. Then we're talking about the amount of pressure that it exerts because of that, okay? So there is a pressure as a result of this water flowing across here. You with me? If I move water over here, what kind of pressure do I need along this membrane to keep everything balanced? Got it? That's the way you define it. Practically, a little more complex than that. All right. Now, let's go back to this illustration a minute, because the next kind of colligative property I want to talk about is called vapor pressure. Okay, vapor pressure. All right. This surface area is the surface of a liquid. Okay, now our surface area, we said pressure is the force acting on an area. This surface area is the surface of a liquid. Okay? So inside this liquid are, let's just say this is water as an example, but it could be any kind of liquid. All right? So some of these water molecules will be, first of all, the kinetic molecular theory of gases state that we assume all the particles in the gas are moving at the same rate. Okay? We know that's not true. All right? One of the things we said about all those assumptions of the kinetic molecular theory of gases was that none of those assumptions are truly accurate, but we assume them to be true because it makes the math of our equations easier. All right? The same is true with solutions. In this kinetic molecular theory, you assume all the particles will be moving at the same rate of speed. That's not true. In any sample of water, you have a lot of water molecules moving at about what we would expect them to be moving to have that certain, whatever the temperature is. But some of them are moving slower, and some of them moving faster. If we were to do a graph where we graph the rate at which each of these water molecules are moving, we get a bell curve. And y'all are all familiar with bell curves, right? Where most of the water molecules are moving about the same, kind of in the middle there where the top of the bell curve is located. Okay? But some of them are moving a lot slower, and some of them are moving a lot faster. Okay? So some water molecules are moving pretty fast. And if they're pretty near the surface and headed in the right direction, those fast-moving water molecules are going to escape and become a gas. Or truly, not really a gas, but a vapor. Okay? They're not really a gas unless the temperature is above the boiling point, or at least at the boiling point. You don't really have a gas unless the temperature is at or above the boiling point. You have a vapor. Okay? So there are water molecules all the time moving fast enough to escape from the surface or through the surface, and that's called vapor pressure. The pressure of those gas vapor molecules escaping across that surface, that's called vapor pressure. The pressure exerted by those particles that are moving fast enough that can penetrate through there, that's called vapor pressure. What vapor pressure is?
Yes, sir.
Write out a definition?
Yes,
Yeah, I can do that. So the definition we're going to use here is the pressure exerted by molecules of a liquid as they cross the surface of a liquid and enter the vapor phase. A more complete definition of vapor pressure would be pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases. Condensed phases would be solid or liquid at a given temperature in a closed system. Now, let's go back to this a minute. The more I heat up the liquid, would you expect more or less or the same number of particles to escape into the vapor phase? More, right? Because you heat them up, they evaporate faster, yes? Until you keep heating it up and it starts to boil, right? After that, you can't really make it any hotter. Okay? All right. Which brings us to a new definition of the boiling temperature. New definition of boiling temperature. Okay? Because in opposition to this vapor pressure is what's keeping this liquid in liquid state. The only reason we have liquids on our planet is because we have atmospheric pressure. In the absence of atmospheric pressure, substances can only exist in solid and gaseous phases. Without atmospheric pressure, substances can only exist as a solid or a gas. Okay? So in opposition to this pressure of vapor is atmospheric pressure pushing down. Okay? You got atmospheric pressure pushing down. When you increase the temperature of the liquid, to the point where vapor pressure equals atmospheric pressure, then you have the boiling point. When you increase the temperature of a liquid to the point where vapor pressure equals atmospheric pressure, you have the boiling temperature of the liquid. When you increase the temperature of a liquid to the point where vapor pressure equals atmospheric pressure, you have the boiling temperature of the liquid. There, if this is a solvent, and I'm going to add solute particles in there, like table salt, like sugar, whatever, they sort of block the way of these escaping vapor particles. Okay? They evaporate slower. They also boil at a higher temperature because it's harder for those particles to escape. Therefore, you're decreasing the vapor pressure. Adding solute to solvent decreases the vapor pressure and increases the boiling point. Well, it decreases the freezing point, yes, but that doesn't have to do with this illustration here. Yeah, when you add solute to solvent, you block the escaping vapor particles, lowering the vapor pressure, increasing the boiling temperature. When you add solute to solvent, you block the transition of those particles from liquid to vapor. You therefore decrease the vapor pressure and increase the boiling point, because boiling point, remember, is reached when vapor pressure equals atmospheric pressure.